You ever see something in nature, some kind of pattern, and just wonder, how does that even work? Well, today, we're going to dive into exactly that. We're talking about system dynamics, and we're going to use one of the most classic examples out there, that eternal dance between predator and prey.
So let's just jump right to the end result first. What you're looking at, this is a simulation. It's tracking wolf and moose populations over like 200 years. And you can see it, right? That pattern. The numbers go up, they go down, all tangled together in this rhythm. It's pretty mesmerizing, but here's the thing. It is not random. Not at all. There's a hidden logic under the surface driving this whole thing.
And that right there is the big question for us today. I mean, think about it. In the real world, you've got weather, disease, all kinds of chaos. So how can a system like that create such a clean, predictable pattern? Well, the answer, it's actually way simpler than you think. And we're going to prove it. We are going to build the model that makes this exact graph right from scratch.
All right, so if we want to understand the result, we've got to look at the engine, right? Let's pop the hood on this virtual ecosystem of ours and see what all the moving parts are. Okay, so this is our blueprint. I know, it might look a little weird and abstract at first, but trust me, it's an incredibly powerful way to see how a system works. It's called a stock and flow diagram. And the best part? It's really only built on two main ideas. Just two. Let's break them down.
First up, we've got something called a stock. Super simple concept. Just think of it as, well, anything that can build up over time, like water in a bathtub, or maybe money in your bank account. For what we're doing here, our stocks are just the animal populations themselves, the total number of moose and the total number of wolves. That's it.
In the second idea, that's a flow. And a flow is just what it sounds like. It's what makes the stock change. So, back to our bathtub analogy, the faucet filling it up, that's a flow. The drain emptying it out, that's another flow. For our animals, it's exactly the same idea. The flows are the births, which, make the stock go up, and the deaths, which make the stock go down. See? Simple.
Now, here's the key thing to get right now. Each population, each stock, has its own flows. The moose stock goes up with moose births, down with moose deaths. And it's the exact same story for the wolves. So right now, they're basically two completely separate systems. But what happens when we finally connect them?
Okay, this is where the magic really happens. Seriously, the secret sauce of this whole model isn't just the stocks or the flows. It's about how they affect each other. It's time to look at the actual rules of the hunt, the logic that ties the fate of the moose directly to the fate of the wolves. Believe it or not, the entire dynamic, the whole dance, it all comes down to one dead simple piece of math. You ready? We just multiply the number of moose by the number of wolves. That's it. That one little calculation is the engine that drives the entire cycle. But why? Why multiplication? It's all about probability. It's actually a concept called the law of mass action. Just think about it for a sec. For a hunt to happen, you need two things, right? A predator and a prey, a wolf and a moose. So if you have way more moose, the odds of a wolf bumping into one go way up. And if you have a ton of wolves, the chance of a poor moose getting found goes up. Multiplying them is just the perfect way to capture that relationship. And what's really elegant is this. If either the moose or the wolves hit zero, poof, the whole interaction becomes zero. No moose means no hunts. It just makes sense.
And that super intuitive logic, well, that's what gets turned into these fancy-looking math equations. But hey, don't get scared off by all the symbols. Just look for that m times w part. See it? It's in both equations. For the moose, it's got a minus sign in front of it because, well, getting hunted is bad for the moose population. But for the wolves, it's a positive thing. A successful hunt means more food, which means more wolves. That's all we did. We just told a story about nature using the language of math.
Okay, let's recap. We've got our stocks, we've got our flows, and we've got that all-important rule connecting them. Our little virtual world is built. So, now for the fun part. Let's hit the play button and see what happens.
And there it is. Look at that. It's the exact same pattern we saw at the very beginning. Those incredibly simple rules we set up, births, deaths, and that one little multiplication, that's all it took to create this complex, living, breathing cycle. And that other view, the one that looks like a loop, that's just a different way of seeing the same story. It perfectly traces out that stable, repeating pattern. It's called a limit cycle, and it's beautiful.
So let's just follow one loop all the way around. Step 1, there are hardly any wolves, so the moose population just explodes. It's a moose party. Step 2, but all those moose are basically a giant walking buffet, so now the wolf population booms right behind them. Step 3, now you've got way too many wolves. They start overhunting, and the moose population completely crashes. And finally, step 4, with no more food, the wolves start to starve, and their population crashes too. And that brings us right back to the start, ready for the whole thing to happen all over again. It's that lag, that delay between action and reaction, that keeps the whole cycle going.
So yeah, we've built a pretty cool model of moose and wolves. But this is so much bigger than just animals in a forest. This way of thinking, it completely changes how you can look at the world.
And this, for me, is the biggest takeaway of all. Think about it. We never told the simulation to make a cycle. We didn't program in the up and down part. All we did was give it a few simple, common-sense rules, and this complex, lifelike pattern just emerged. It appeared all on its own. And that idea, the concept of emergence, is one of the most powerful ideas in all of science.
This is such a perfect example of how math is so much more than what we learned in school, right? It's not just about getting the right answer or crunching numbers. It's a language. It's a way to tell a story about how the world works, about the relationships between things. It's a tool for discovery, whether you're looking at an ecosystem, the economy, or even how a disease spreads.
And I'm not kidding, this exact same way of thinking, finding the stocks, the flows, and the little feedback loops that connect them, it's used everywhere. We use it to understand all of these huge complex systems. You know, the boom and bust of the stock market, the way a virus spreads through a population, even climate change. The details are different, but the core principles, they're the same. It is an absolutely powerful lens to see the world through. So, I want to leave you with a question to chew on. The next time you see some big, complex pattern playing out, whether it's in the news, at your job, or just out in the world, stop and ask yourself, could this all be coming from just a handful of simple underlying rules? And what could those rules be? Because if the dance of the predator and prey teaches us anything, it's that sometimes the most complex, beautiful patterns have the simplest blueprints.